So we could also plot the number of electrons that are ejected as a relationship to the intensity. So that was yet another experiment they could do. And this is what they had expected, that there would be no relationship. But instead, here they saw that there was a linear relationship, not to the intensity and the kinetic energy of the electrons, but to the intensity and the number of electrons. So none of these observations made sense to any scientists at the time, and really all of these observations were made and somewhat put aside for several years before someone that could kind of process everything that was going on at once came along. And that person was Einstein, conveniently enough. If anyone could put it together, we would hope that he could, and he did. And what he did in a way that makes sense when all of us look at it is he plotted all of these different metals on the same graph and made some observations. So for example, here we're showing rubidium and potassium and sodium plotted where we're plotting the frequency. That's the frequency of that light that's coming into the metal versus the kinetic energy of the electron that's ejected from the surface of the metal. And what he found here, which is what you can see and we can all see pretty clearly, is the slope of all of these lines is the same regardless of what the type of metal is. So he fit all these to the equation of the line, and what he noticed was the slope was specifically this number, 6.626 times 10 to the negative 34 joules times seconds. And he also found that the y-intercept for each one of these metals was equal to basically this number here, which was the slope times the minimum frequency required of each specific metal. So that's of the threshold frequency. And he actually knew that this number had popped up before, and a lot of you are familiar with this number also, and this is Planck's constant. Planck had observed this number as a fitting constant years earlier when he looked at some phenomena, and you can read about it in your book, such as black body radiation. And what he found was he needed this constant to fit his data to what was observed. And this is the same thing that Einstein was observing, that he needed this fitting constant in order to, that this constant was just falling right out of, for example, this slope and also the y-intercept. So he decided to go ahead and define exactly what it is, this line, in terms of these new constants, this constant he's calling h, which is Planck's constant. So on the y-axis, we have kinetic energy, so we can plug that in. If we talk about what the x-axis is, that's just the frequency of the light that's coming in. We know what m is. M is equal to h. And then we can plug in what b is, the y-intercept, because that's just the negative of h times that threshold frequency. So we have this new equation here when we're considering this photoelectric effect, which is that the kinetic energy is equal to h nu minus h nu threshold of the metal. And what Einstein concluded and observed is that, well, kinetic energy, of course, that's an energy term, and h times nu, well, that has to be energy also, because energy has to be equal to energy. There's no other way about it. And this worked out with units as well, because we're talking about joules for kinetic energy, and when we're talking about h times nu, we're talking about joules times second times inverse seconds. So the very important conclusion that Einstein made here is that energy is equal to h times nu, or that h times nu is an actual energy term. And this kind of went along with two observations. The first is that energy of a photon is proportional to its frequency. So this was never recognized before, that if we know the frequency of a photon or a wave of light, we can know the energy of that light. So since we know that there's a relationship also between frequency and wavelength, we can do the same thing. If we know the wavelength, we can know the energy of the light. And I use the term photon here, and that's because he also concluded that light must be made up of these energy packets, and each packet has that h, that Planck's constant worth of energy in it. That's why you have to multiply Planck's constant times the frequency. Any frequency can't have an energy. You don't have a continuum of frequencies that are of a certain energy, it's actually punctuated into these packets that are called photons. And as you know, Einstein made many, many, many very important contributions to science and relativity, but he called this his one single most important contribution to science, the relationship